Hello and welcome to this Java DSA tutorial. In this chapter, we'll explore the graph data structure. So before you start working on graph-based algorithms, it is important to understand the graph data structure as it has its own nomenclature. There are different types of graphs, and a better understanding of it will help you in solving the algorithms in a better way. So we'll go through some theory to start with. Introduction of graphs. So graphs are actually non-linear data structures which are used in computer programming to represent relationships between entities. Since they are non-linear, that means they are good at modeling complex connections where each element can link to multiple other elements. So because of this flexibility, graphs are indispensable for solving real world problems. So if you have to map cities and transport routes to powering social media networks and recommendation systems, everything you can do with graph-based algorithm, right? So first thing is, as we said, this non-linear data structure. So what exactly are linear and non-linear data structures? So linear structures like arrays, stacks, queues, linked list, these will store data sequentially, where each element has a single predecessor and successor. Correct. Suppose I have this array, right? So every element will be added sequentially. You can go from this side to this side, and for every element, there is a predecessor and successor. One. Whereas with non-linear structure, which are trees and graphs, you have multiple relationships. So node can connect to many other nodes in graphs, right? It will be something like this. So that is the other distinction between graphs and trees. So graph and tree both are non-linear data structures, right? And tree is also kind of a graph, but they generally have some restrictions, right? Like binary tree can have only two children, and they have a hierarchical structure. You'll have one root in the beginning, then you have children, and you won't have cycles because there is no connection between siblings like this. You won't have, so there is no chance of having a cycle in a tree. Whereas with graph, you can have multiple connections, right? If you see here, A is connected to B, to C, to E, and there is no strict hierarchy. There is no root here. You can start from anywhere to go anywhere, correct? And it can have cycles also. In this also we have this cycle A, E, D, C, A. Now we come to some of the nomenclatures of the graph, which is very important to understand actually. So here nodes are actually called vertex. That is the fundamental unit of a graph representing an entity. So here if you see, this is a vertex, A is a vertex, E is a vertex, and in this graph if you see A, B, C, D, E, there are 5 vertices. So that is your vertex. Then we have link between two vertices, that is called edge. So it can be directed or undirected. Here it is undirected. So you can go from A to B and you can go from B to A also. So both way you can travel in this, right? In this connection, A to B. Then you have adjacent vertices, which is neighbors. So two vertices are adjacent if they are directly connected by an edge. So if you see here, A is directly connected to E, C, and B. So that means A is adjacent to C, B, and E, whereas B is only adjacent to A, correct? Then you can also calculate the degree of a vertex, which is actually the number of edges connected to a vertex. So you can have a in degree and out degree. In degree is the number of incoming edges, out degree is the number of outgoing edges. So here A is connected to B, C, and E. That means in degree is 3, right? Then you have path. So sequence of vertices connected by edges. So this is one path here, right? A, C, D. I can go from here to here. That is one path. Or A to B, that is also one path. Then cycle is if a path that starts and ends at the same vertex. So here if you see, we have one cycle A, C, D, E, A. We start from A, we end up at A. So there is a cycle in this graph. Then we have connected graphs also, where every vertex is reachable from any other vertex. Then it is a connected graph. So this is a connected graph actually, right? I can go to any other vertex from any vertex. From E, if I have to go to C, I can go like this. If I have to go to B, I can go like this. From B, if I have to go to D, I can go like this. So I can go to any other vertex from any of the vertex. So it is a connected graph. Then we have different types of graphs also, which is very important again, because your algorithms will depend on it, which kind of graph. So logic may change a little. So first thing is we have directed and undirected graph. Undirected graph where edges have no direction. They simply connect two vertices. So you can go both way with undirected. Like here, as I was telling, right? A to B, B to A, both direction you can go. Whereas with directed graph, edges have a direction and you generally show it with an arrow. Wherever your arrow is pointing, that is the direction you can travel, not the other way around. So here I can go from A to B or A to C, but C to A is not permitted. Then we have weighted and unweighted graph. Unweighted graph is where edges are treated equally with no values in that. So here whatever we saw, that was a unweighted graph. Weighted graph is where we'll have some numerical values called weights assigned to the edges. Now this weight may depend on the scenario, right? It may be any value. For example, if these are cities, then it may be distance, time taken, or fare or cost, whatever it takes to go from one city to another. So for weighted graph, you may have to do some algorithms, right? Find the optimized path based on time, or shortest path by distance, or fastest path where you can take less time. So then you will have weighted graphs. There is also cyclic and acyclic graphs. So cyclic graph is a graph where you will have at least one cycle, right? Acyclic graph is a graph which has no such path, so no cycles. Then you can also have connected versus disconnected graph. Connected graph that we have already seen, right? Where every vertex is connected to any other vertex. You can go from any vertex to any other vertex. Whereas in disconnected graph, you won't have that facility. So suppose I have this to separate like this. This is a disconnected graph. I can't go from this to this or this to this. Then we have sparse and dense graphs. A sparse graph has relatively few edges compared to the maximum possible, whereas dense graph has many edges close to the maximum possible. We go back here again. Right, this is kind of sparse. If we connect this also, this to this also, this to this, then it becomes a dense graph if we start connecting everywhere, right? So we have these types of graphs. Then, of course, graph is a very important data structure. So we can see some of the practical usage of graphs. Any navigation system, Google Map, all that will be using the graphs, where cities and roads are modeled as vertices and edges, right? So you'll use a weighted graph where you can use a algorithm like Dijkstra's or A star to find the shortest or fastest route, right? Then network routing also uses graph based algorithms. So our internet, which we use, right? So you'll have many routers and servers, right? They are connected by edges. So that will also use a graph to find out how to send data packet in a optimized way, right? It will determine the efficient paths for data packets so that data reach faster and you don't have congestion across networks. Then any dependency resolution, so any build tool like Maven or Gradle or even your compilers all create a graph based, right, dependency graph they'll create, and they'll traverse that dependency graph so that they know, okay, if I'm coming to this class, it is dependent on these other classes. That means when I'm compiling class A, suppose it is dependent on B, C, and D, that means B, C, and D should already be compiled. That dependency graph it will create, and based on that it will do that dependency resolution. Then of course your social media, where again graphs are used quite extensively. All your connections, right, friends, likes, follows, all that is represented as a graph. So these are some programs, beginners you can say, where you can start using graph. So first thing is, how will you represent a graph programmatically? So graph adjacency representation. You can do it using matrix and list. With weighted graph, you have to store weights also when you are creating a adjacency representation for the graph. Then of course, adding or removing a vertex in a graph with its edges. Then you can do graph traversal, DFS or BFS, detecting a cycle, whether a graph has a cycle or not. Then you have a minimum spanning tree, shortest path. There is also Pascal's algorithm along with Prim's algorithm for that. And there are many more actually. So these are the algorithms we'll try to do with graph. But all this is also important. So this chapter only covers some theory about graphs and nomenclature, which you will see quite extensively used in graphs. So please go through it and keep that in mind. Thanks for watching the video. Please don't forget to like and subscribe.